Hello everyone, I'm Xinlei Niu. I'm going to introduce our paper, Latent Optimal Path by Gumbel Propagation for Variational Bayesian Dynamic Programming. It is a joint work with Christian, Jean, and Charles. The generative task is very popular recently. Many generative tasks may require to model the structural dependency between conditions and the data, such as speech, music, and language synthesis. This structural dependency is usually unobserved but important, which can potentially improve the interpretability and effectiveness of the model. One solution for capturing the structural relationship is finding an optimal path in a graph. This problem usually solved by dynamic programming that break it down into several subproblems and find the optimal solution within the subproblem iteratively. Dynamic programming algorithm is non-differentiable, since it uses the max operator. To engage it into neural networks, previous methods solved the problem by using soft approximations involving convex optimization or adding a convex regularization in loss functions. For applications on downstream generative tasks that require to obtain unobserved structural dependency, some of them separate multiple training strategy that the model strongly relies on outputs of a pre-trained model, or making a strong assumption on the model structure, or alternatively, use soft approximation for training but the hard assignments for inference that cannot ensure the train and test consistency. Instead, we propose a probability softening solution to seek an optimal path in a graph. We call it stochastic optimal path. In this case, we define every possible path in a directly acyclic graph and follows a Gibbs distribution. We denote a distribution family D with parameter R, names the DAG, age, weight W, and the temperature parameter alpha. However, the denominator in this equation is intractable. Therefore, our goal is to define a unified method to obtain a structured sparse optimal path and provide an alternative tractable closing form for variational Bayesian inference for capturing an optimal path. Thereby, this allows the gradient optimization in probability generative frameworks. Before starting our solution, I would like to introduce the definition of a DAG. We denote a directly acyclic graph with nodes V and age E. The nodes are numbered in a topological order such that the V starts from 1 to n. We assume 1 is the only node without parents, and the n is the only node without children. We also denote the age-weight matrix W and set the negative infinitive to the elements that not belongs to the age set. We denote a capital Y V1 to V to be a set of all paths from the nodes 1 to V. For each path, Y has a score by summing age weights along the path. Then, I would like to introduce the property of Gumbel random variable. Denote a uniscale Gumbel random variable with a location parameter mu and the PDF. The Gumbel random variable satisfies three code forms in shifting, max, and argmax operator. Recall to the denominator in the Gibbs distribution is intractable. We'll make use of Gumbel property to offer an equivalent formulation. We denote a Gumbel distribution GY with location parameters mu equals to 0. Thereby, all the optimal path Y will follow the Gumbel by the Gumbel shifting property. Now, let's extend its solution to all partial paths and define QV. The motivation for constructing QV is to allow us to set up a recursion on the entire DAG. By this definition, we can state our main result. The location parameter μ(v) for each node v can be obtained by a recursion. Since we obtain the location parameter for each node, we can then obtain a transition probability from a parent node v to a children node u by this closing form. Based on this finding, we can sample stochastic optimal paths according to transition metrics starting from the last node and reversely until the nodes equals each to 1. And an alternative tractable likelihood of a stochastic optimal path. We also define the closing form for the k-out divergence within the distribution family of Gibbs distribution. This allows gradient optimization for learning edge weights, thereby obtaining the latent optimal path. Since we have all integrants for variational Bayesian inference, we now showcase an extension of the Bayesian dynamic programming into a variational autoencoder framework, namely BDP-VAE. BDP-VAE framework allows to find the latent optimal path between the condition and the data in a latent space by learning the edge weights. This helps downstream tasks that require unobserved structure dependencies to be end-to-end pipeline and, at the same time, maintain the sparsity of dependencies and the train test consistency. We now showcase how the BDP-VAE framework applies to downstream tasks. We first adopt a non-end-to-end TTS model, the fast speech 2, to BDP-VAE framework, and we call it the BDP-VAE TTS. BDP-VAE TTS is an end-to-end pipeline make the model no longer relies on external pre-trained models, thereby improve the model performance. Meanwhile, BDP-VAE ensures train and test consistency on finding the monotonic alignment path compared to the existing end-to-end TTS model. The second application is the end-to-end scene voice synthesis. Our model captures the monotonic dependencies and improves the model interpretability between conditions and the synthesis outputs. At last, we verified the behavior of the latent optimal path in the BDP-VAE compared to the random baseline on a dataset with ground truth dynamic time warping path. BDP-VAE achieves closer alignment with ground truth. This indicates its effectiveness in finding a latent optimal path. Thanks for listening. Our code and paper now is open, public available. Thank you.